Hello, thank you for joining us on our presentation on grammar-based directed testing of machine learning systems. My name is Sakshi Udeshi, and this work was done with my advisor, Dr. Sudipta. We are from the Singapore University of Technology and Design. Okay, let's get into it. Let's consider a sentence. My house is on fire. Please send help in Sebastopol, California. There's a huge forest fire approaching the town, which is a possible scenario given today. If we want to automate the emergency response, we need to know that this will be directed to the appropriate departments. But the outputs for certain ML systems is like this, which is hobbies and interests, science, arts and entertainment, home and garden, religion and spirituality. This is not ideal. So to combat this, we want to abstract natural language for testing. Let's say this is the input space, which is a huge input space for any NLP product. And this computer represents the NLP product. The blue part represents the training data, red part represents the test data. What we want to do is abstract this large input space. And we do this using a context-free grammar. There are two things we leverage to find violations. Let's say that this white area is the output space. We leverage the concepts of robustness and differential testing to discover violations. In the abstracted input space, let's say an input given to two NLP models with the same goal have vastly differing outputs. This is a violation. We use robustness to discover similar violations in the same area as this input. So the red input in this case is a similar input which goes to both of these NLP systems and produces similar outputs. So what is a violation? In the output space, if the two output sets overlap significantly, then it is not a violation. If they don't overlap too much, then it is a violation. How do we formalize this notion of violation? We use something called the Jaccard index. For any two sets, Jaccard index Ji is defined as the cardinality of the intersection of two sets over the cardinality of the union of those two sets. This ratio is always between 0 and 1, and if A and B are both empty, we define Ja, B as 1. The lower the cardinality, the lower the Jaccard index Ji, the more differing these sets are. And we say that this is a violation if they're below some input below some threshold J. So how do we direct the search? Let's say this is an example grammar. Using this grammar, the derivation tree for a sentence, Mary saw my dog, looks like this. At this derivation tree, we will take a terminal symbol, find the production rule that is responsible for this terminal symbol, and replace this terminal symbol. Let's say we replace this terminal symbol with Bob, but then the violation is no longer there. This is not a violation. So we revert back to Mary, we pick another terminal symbol and replace it with some new terminal symbol. And this is how we perturb the inputs to generate more inputs and also direct the search. Let's visualize how this works. Once we have an input, we will randomly explore till we hit a violation. The violation region is usually, we want to be in this region. So if we go out of this region with a perturbation, we will come back. We will cancel that perturbation and explore other areas. Similarly, we go back out again, come back. It's as simple as that. And what do we mean when we say similar sentences? Consider these two sentences from two distinct grammars. Mary saw my dog and Frank saw my dog. Because these two sentences do not have the same derivation tree, these two sentences are not considered similar sentences. As a result, we cannot mutate Mary saw my dog to Frank saw my dog. Now, how do we experimentally validate our setup? We considered three major classifiers: Rosette, uClassify, and Alien, which are industrial classifiers used by companies such as Amazon, Pinterest, Dell EMC, Microsoft, Airbnb, and Oracle. We also use a very specific NLP classifier whose output is constrained within this IAB content taxonomy, because we need classifiers who have similar outputs. And we only use the top tier classification for our experimental setup. Can the robustness be leveraged systematically to test real-world classifiers? Was our first RQ1. Turns out it can. Once OGMA, which is the name of our tool, finds an error, it tends to stay in that error state for a long time. If we zoom into this picture, between iterations about 140 to 300, we get to see that once OGMA finds an error, it tends to stay in that error state for a long time, whereas the random error state keeps flip-flopping. How effective is OGMA in terms of generating error-inducing inputs for real-world classifiers? For the pairs of our classifiers, the error rate of OGMA, or the errors discovered by OGMA for a given number of iterations, is clearly larger. The number of unique inputs generated and the number of errors generated in both cases, in all three cases, is always larger. How sensitive is OGMA with respect to J? So the lower the Jacquard threshold, the more difficult it is to find errors. And the higher the Jacquard threshold, the easier it is. The reason is, if the Jacquard threshold is high, any difference between the two outputs will cause the classifier for it to be an error. And when it's lower, they need to be significantly different, the output sets, to for the input for it to be classified as a violation. How sensitive is the grammar with respect to the chosen, with OGMA with respect to the chosen grammar? We chose 6 distinct grammars, and in all cases, OGMA performs much better than a random approach. We also use these error-inducing inputs to retrain a small classifier, and to show that we can decrease the number of errors after retraining using our OGMA approach. So to conclude, we abstract an input space, we leverage differential testing and robustness, and we direct the search. And it depends on the grammar what sentences are considered similar. Thank you. I hope you have a good day.